to welcome our next speaker, Professor Ivan Remizov, who will give us a presentation on Chernoff approximation for resolvents of generators of C0 semigroup. As normal, we would like to keep it 25 minutes for presentation and 5 minutes for question and answer. Thank you, Professor.
Thank you. Well, as usually at that conference, being an organizer, I have not enough time to prepare slides for my talk. So as before, I will be giving the talk commenting my abstract. You can find it on the website of the conference. And I will just give comments on the abstract. Is it visible? Is it readable?
Yes, absolutely.
Good. We have here 3 pages, which is the maximum recommended volume of the abstract. And well, I first will comment the title. Chernoff approximations are used to find a semigroup, C0 semigroup. And they provide solutions to evolution equations because C0 semigroups provides such solutions. And today I would like to show a very simple idea which I found myself, but probably if someone will point out me, probably this is not my finding, probably someone used just this idea before. However, I suppose that it is new idea, but based on very simple fact. Evolution equations are, examples of them are parabolic equations, Schrödinger equation. And I would like to say a few words about applications of semigroups and of Chernoff approximations of semigroups for solving not parabolic but elliptic equations. That's it. So this was the preamble. Now I'm going to the main part. So the summary of the talk is the following. I will just read the slides because otherwise it will be difficult for you simultaneously to read the slide and to follow what I say. I will just read the slides. Please, at any time, you're welcome to interrupt me. You're welcome. If someone will ask a question in Russian, I will reply in Russian. Good. So the method of Chernoff approximation. Here is the link to the very nice overview written by Yana Budko. It was written in 2017. Then some time the publication took. Since that time, there is some progress in the Chernoff approximations. For example, Oleg Galkin and I developed a theorem which allows to prove estimates on speed of convergence of Chernoff approximations. Alexander Videnin, my PhD student, made together with me examples of fast convergent Chernoff approximations. And well, also some other research was done, but still this is a good overview. So those who are interested in Chernoff approximations, you are welcome. So method of Chernoff approximation is extremely effective tool for expressing the exponent to TL in terms of variable coefficients of operator TL. If operator L is bounded, then exponent can be defined as a power series which converges in operator norm. If operator L is not bounded, then power series is not such a good object. But there are unbounded operators that still possess the property that exponent of that operator exists. Such operators are called generators of C0 semigroups. This is not a formal definition, just explanation. What does it mean? So here, in that notation, I use to show that L is an infinitesimal generator of C0 semigroup, which I denote with e to the power TL. And expressing exponent to the operator TL in terms of coefficients of operator TL is not an easy task, because the formula for it is not applicable directly, because you cannot use power series. So other methods go to the to the desk, and I used to calculate this exponent. And one of the methods is Chernoff approximation, which if we have differential operator L of any order with variable coefficients, indeed allows to express this exponent as explicit formula in terms of coefficients of operator L. By the way, let me check how much time I have. Aha, good. Good. So I should finish in 40 minutes. That's it. In the talk, I will show that this method can also be used for expression the resolvent of that operator in terms of variable coefficients of operator L, and for finding solution of the corresponding differential equation, this equation. For example, if L is second order differential operator acting on the space of functions that maps, say, Rn to R, then this is an elliptic equation for function f. If L is a differential operator that maps on the set of functions that maps R to R, then this is the second order ordinary differential equation. Is it clear?
Yes.
Good. So we demonstrate this, I mean this method of expressing the resolvent on the second order differential operator L. However, other operators are also can be managed with this technique. And as a corollary, we obtain two new representations of the solution of an inhomogeneous second order linear ordinary differential equation in terms of functions that are coefficients of this equation that play the role of parameters of the problem. And this reasoning also works in the multidimensional situation where we have an elliptic PD instead of ODE. Full proofs are available in the preprint on archive. You are welcome. Let us recall the Chernoff theorem. There are many wordings of Chernoff theorem. Paul Chernoff originally proposed his theorem for contracting semigroups. Then there were many improvements of that result. I will use this wording because it will be it will go in line with the main theorem that I would like to show today. So suppose that the following three conditions are met. First, we have a C0 semigroup with generator L in Banach space F. And for some omega, this inequality holds for all t. Such semigroups are called quasi-contractive. If we add here multiplier m, which can be greater or equal than 1, then those semigroups are of general sense. And such inequalities with some constant which is greater or equal than 1 here are satisfied for all semigroups. So this is a slight modification, but also there is a Chernoff theorem with m here. Second condition, there is a strongly continuous mapping, which means it is continuous on every vector. So S of t for each t is a linear bounded operator in Banach space F. So for each vector f, here we have it. For each vector f, s and each number t, S of tf is a vector in f, and if we fix f and change t, then it will be a vector valued function of number parameter t, taking values in Banach space f, and we can speak about continuity of such function. And if this function is continuous, then they say that the mapping S is strongly continuous. What does it mean, this condition? Continuous on every vector. Also at 0 we have identity operator, and the same inequality holds. Next, there is a dense linear subspace in F such that for all vectors F from this such subspace, the following limit exists. It is natural to call this limit the derivative of S at 0, and well, it is widely used notation. It is as it is a linear subspace in Banach space, then we can ask if this operator S prime of 0 is linear, and due to the properties of the limit, we can show that it is linear indeed on this subspace. So we can define linear operator which maps F to F with domain D, which is a dense linear subspace in F. And we can ask if this operator is closable. And if it is closable and its closure coincides with the generator of the semigroup, then this condition is fulfilled. Informally, this condition that S of 0 is identity, and this informally it means that S of t equals identity plus TL plus O small of t. Then the following condition holds. I call it condition C because of Chernoff. Condition is the following, that for each f and n tending to infinity, we have that convergence, that S of t over n to the power nf tend to e to the power tlf, locally uniformly with respect to t, which means that for each t greater than 0 in each vector f, the limit of supremum of the norm of the difference tends to 0. That's it. Here about the notation, this is a composition of n copies of linear bounded operator defined everywhere on F, because for each t, S of t is a linear bounded operator which maps f to f. So if we substitute t by t over n, then it again will be for each t and n linear bounded operator, mapping f to f, and we can make composition. That's it. The following definition is widely used, that if we have a C0 semigroup and we have a mapping S, then this mapping S is called Chernoff function for operator L, and also sometimes Chernoff function for the semigroup e to the power tl, if it satisfies condition C of the Chernoff theorem. And also that equations are called Chernoff approximations to the semigroup. Sometimes not condition C is used to say that function, operator valid function is a Chernoff function. Sometimes conditions 1 to 3 are used. Chernoff theorem is not directly invertible, but close to invertible. So as for me, I select this one. That's it. And now the main idea of the talk. So thanks to the Chernoff theorem, we have, we have that convergence for all vectors f and for properly selected operator valid function s, which is Chernoff function for operator L. Also, there is a standard fact that for lambda with the real part of lambda large enough, in our context, it means that lambda should be bigger than this omega. For all lambda with real part large enough, we have the following representation, that the resolvent of operator L can be expressed via the semigroup generated by operator L with this formula. This can be said that the resolvent is the Laplace transform of the semigroup. So this, what can we do? Here we can substitute the semigroup by Chernoff approximations of semigroup, and then get approximations for the resolvent. So here I used colors. This red equality is a classical fact, very well known. This green equality holds due to the Chernoff theorem, because I substitute here, yes, the Chernoff theorem. I substitute the semigroup applied to F to the limit of Chernoff approximations applied to F. And here, this blue equality is the main idea of the all results that will follow, that we can put the limit outside. It is not very difficult to prove. In general case, proof uses that Chernoff convergence in Chernoff theorem is so nice that we have this property, and this is just enough to prove that we can change order of integral and limit. So the main idea is this one, is that we can make Chernoff approximations for the resolvent if we use representation of the resolvent via integral transform of the semigroup, and then substitute semigroup with its Chernoff approximations. Everything else is just a corollary, and you can use this idea in many situations. I provide one general theorem, and also two theorems with examples, but they are, from my point of view, less important than this main idea, because it is a simple idea. You can apply it whenever you want and adjust it to what you have. So is that clear? If you have
Yes.
questions at that stage, at that step, please ask.
Sure.
Okay, so
I
now,
have a question.
please.
You consider Banach space. Would be this theorem in fresh space on locally convex space?
I have not tried. I just have not tried, and
It's be interesting. This method of Milyonchikov to differential equation in these spaces, and it's possible to method of Milyonchikov is possible in these cases.
well, you are welcome, you or your students. I think I'm not interested in going in a more general setting than
More
Banach space.
general space, yes.
Yes, I'm not interested. This means that you are welcome to attack this problem. Just using my idea that we can change the semi-group substituted by the resolvent. More questions? No. Okay, then I proceed. So here is a general theorem which says that suppose we have Banach space, set of all linear bounded operators. We have operator L, and C0 semigroup satisfies the general condition for C0 semigroups, which is not restrictive because for every semigroup there exists some constant m and omega that is satisfied. Suppose we have function which satisfies this condition, which is also not restrictive, and for example, if norm of s of t is less or equal that than e to the power omega t, then this condition follows from what I said. And let us denote by symbol lambda the resolvent. Then if we have that condition, you see this is a corollary of Chernoff theorem. So if S is a Chernoff theorem for operator L, then we have that convergence. So indeed, those approximations, which I can call Chernoff approximations for the resolvent, indeed they converge to resolvent. If we have even more powerful condition, which are not always obtainable, where we have uniform convergence of uniform, I mean in F, such convergence in norm space were obtained by Valentin Zagrebnov in several cases. Then we will have that type of convergence. Here the difference is only F. Now two example theorems. First, suppose we have that ordinary differential equation. If we use the integral based Chernoff function, then Chernoff approximations will be this one. So solution to that equation is given by this formula. Here we see multiple integral with multiplicity tends to infinity. So this is a Feynman formula. Such expressions are called Feynman formulas that are limit of integral will multiplicity tends to infinity. So one can try to interpret it as some Feynman integral over some set of functions For example, Professor Shevgulidze, who asked the question, is a true expert in Feynman integrals. So here what we have, we see that at first time, solution to ordinary differential equation is represented as a Feynman formula, and maybe it can be interpreted as a Feynman integral. And so here you see coefficients A, B, C, lambda, J, and they all appear here as parameters in formula for the solution. Very nice. If we use for the same equation another Chernoff function, which is uses shifts, uses shifts, then you can express solution of the same equation using those shifts operators, integral of Chernoff approximations. And here for that Chernoff function we obtain the estimates, so we can say a few words about the estimates. Here we have general fact about speed of Chernoff approximations of the semigroup, and here we infer from it the fact the speed of convergence of Chernoff approximations to the solution of this equation. So this is well prepared for the numerics. Also, we can substitute integral over infinite interval by integral over finite interval with controlled level of error. And I will finish with the final remark that independently of Chernoff function that we use, it is based on integral operators in the theorem 2, or here based on the translation operators, here those operators. Anyway, Chernoff approximations are allowed to calculate the solution only in one point of the domain, in one x, in our example. So here, see f of x. F of x is equal to this. Meanwhile, methods based on computational grid calculate values of the solution in all points of the computational grid. So if you need only one solution in only one point, then you can use Chernoff approximations. It may give some time economy. Moreover, values of Chernoff approximations at different points of the domain can be calculated in parallel using multi-core processors or GPU, which is advantage of this approach. However, still the computational complexity is not very high, so still we have something to do with it, but nevertheless, I would like to just to mention these advantages of the method of Chernoff approximation. I am out of time, so thank you.
Thank you, Professor. Thank you, Professor, for your great presentation. Now we are open for Q&A, for question and answers.
Well, probably.
I have a question. Yeah. Do you have any? I mean, can we consider like? I mean, when you are saying that it's only for one x, when if we have a singularity at the point that we are investigating, what will happen?
I don't understand your question.
If you have for example, you are saying that this
here.
Yes, if we had a singularity.
What do you mean by singularity?
for example, if there is a blow up at one point.
Oh, blow up in coefficients.
Yes.
Which coefficient?
Um. Mm, I don't know. Maybe. Maybe it's a bad question. Sorry.
No, that's not bad question. For me, functions are from some function space. At that, here we use a space of functions that are continuous, vanish at infinity, and I work in that space. And for coefficients, we have these restrictions. So they are very nice, no blow ups. And at that case, my coefficients are uniformly continuous and bounded. So they and the solution f is the same, uniformly continuous and bounded. It may not have limit 0 at infinity, but the same setting, if you prove that this S is a Chernoff function for a semigroup defined by the same operator L. So here, oh, it is A here. This one. If this semigroup is indeed a semigroup, say in the space LP, L capital P, then we can ask if this Chernoff, this function is indeed Chernoff function for the semigroup in LP, for example, in L1, L2, L capital 1. Then that functions can be unbounded, and then we can use it for singularities also, depending on the space, because this idea, it works in any Banach space. If this Banach space contain functions that blow up, well, okay, you can use it.
Okay, thank you so much for your comprehensive answer.